Hello, my friends. We touched on this slide this morning, and or Friday morning. Friday. Let me start over. No, I'm not going to start over. I'm just going to roll. So, we touched on this slide on Friday at some point, and the deal here is, sure, we've gotten to this case where we've seen that things that behave like waves sometimes behave like particles. I.e., or is it e.g., photons. Light sometimes behaves like a particle. Light we think of in many cases like a wave, also can behave like a particle. Well, it also can be true that sometimes things that are particles can behave like waves. And that's what we had to apply this morning in what we call the de Broglie hypothesis. All right. Yeah, it was this, if you remember, we did that quantization of what we called angular momentum. You do not have to know that for a test that we take in here or the AP exam. But, it basically said that electrons, can behave like waves or have to have wave properties in order for some conditions that Bohr saw in his observations to be true. All right? And so we were able to justify why these orbits or why these radii would be where they were based on the fact that an electron with a different energy, we can relate energies to wavelengths. And therefore, we also said that, in this first orbit here, it's impossible to draw this one, but if this thing was like a string, well, on that string, you'd have to have a full wave because they sort of applied some standing wave characteristics to these things where, I don't know if this is really true, if I've said this quite the right way. Yeah, you know what? Let's just do that. Because standing waves interfere alternatingly, constructively and destructively, all right? So we'll just say that electrons have what's called a wave function, something called the Schrödinger equation that describes the wave function of any system. And that wave function for these, what do you call them, these electrons must behave like standing waves. All right, so if this was a string, right, we go from the circle like that to a string like this, we'd get one wavelength on that string. Okay, now notice if we take this one, then we have a bigger circle. That means it's a longer, like a longer string. And this is not string theory, so don't get all geeked up about string theory. Get geeked up all you want, but yeah, it's not about that. Actually, I got to make this even longer. So this one is like a bigger string where not only do we have to have two waves on it, but they're also twice as long. Notice that up here? Two waves twice as long. So we go, let's see, one wave like that, two waves like that. And notice, so up here, this is like, check it out. If this is the plain old circle, right? This is peak, and then underneath trough, and peak and trough. Got that? And here, right, here's trough and peak, and trough and peak, and trough and peak. And so with that third orbit, we need 3 standing waves of a wavelength that's 3 times as big as this one. All right, and that really gets us to the idea of, for this third one, for n equals 3, that means that the circumference of that third orbit is, well, 9 times the circumference of the first one, because it's made up of, well, 3 times as many waves, which are also 3 times as long as this one. So there's 3 times 3, or 9 times as bigger. And that agrees with this thing. If their circumference is 9 times as big, it agrees with our expression for that any radius of state n goes as n squared times what we call the Bohr radius. An awesome job today, this Friday, with that derivation. I'm preemptively saying you are awesome, Block 4. I have no doubts you'll be awesome. Okay, so the bottom line, particles can and do exhibit wave properties. Okay, and come on, we can say, furthermore, that every particle has a wavelength, and that wavelength depends on its momentum. We say that any particle's wavelength is h over its momentum. Okay? So this is an equation you're going to have to use. It's in the reference table when it comes for exam time. I totally get this. This is really kind of out there stuff. All right? But we can take a particle. If we know its wavelength, if we know its momentum, we can express what we call its de Broglie wavelength. Okay? It means for the Bohr model, well, it means that. It makes us able to justify that. Fair enough? Okay. Yes, this is not in the same order as your slides, but here's something way awesome. It's called the Davison-Germer experiment. And we have seen that, well, we've seen diffraction gratings, right? Diffraction gratings are things like this with basically lots of slits, and we shine light in there, and then that light can deflect out to different angles, and there's this whole thing with theta and a little path length difference there and all that stuff. So waves show well, diffraction, right, and kind of multiple source interference. Well, what Davison and Germer did was they took this nickel lattice, this nickel crystal, all right, and the lattice means that the what do you call them? The atoms are spaced very uniformly, right? And they have spacing just like the spacing of slits in a diffraction grating. Okay? And what these guys did was they fired electrons at this nickel crystal. And based on their speed, right? Again, we can say that lambda is h over p. Based on their speed, they had some theoretical de Broglie wavelength. All right, they are particles, right? But they fired them at this crystal, and what happened was they scattered out to a bunch of, they bounced all over the place, right? But a lot of them, a ton of them, scattered out at this angle, 50 degrees. So what they do is literally you put a detector on a little arm that you can swing around like this, and it makes a little clicking sound, or it registers, these are electrons, I guess, it can register a little bit of current when electrons hit it, right? And when they swung that detector out to this angle, it registered a lot of current. And so tons of electrons were scattering out, what we call scattering, out to that angle. All right? Well, that agreed really, really closely with an idea that these particles were just like waves with certain wavelengths being shot at a diffraction grating with spacing d. All right, notice, here's our diffraction grating type of stuff, d sine theta. Right? Lambda is d sine theta, path length difference. And we said, okay, based on where they scattered and how far apart these nickel atoms are, or nickel nuclei, I don't know, nickel atoms, it said, well, it seems like the wavelength should be, this is the symbol for angstrom, 1.65 angstroms. Right? That's based on if these things were actually waves. Well, where they came out, using this idea of the de Broglie wavelength, it came out that their wavelengths were actually extremely, extremely close to that. So there's some super duper evidence, right, that particles do indeed exhibit wave characteristics. I mean, just why? Oh, look. Remember I was trying to figure out when all that was? Yeah. Now, 1905, I've mentioned the year 1905 a couple of times. I think Bohr model of the atom was actually like done in 1905. I feel like, well, I'm gonna have to look more closely into that. But I think the idea is, it takes a long time to formalize those ideas and get them to a point where people really, really accept them to the point where you can win the Nobel Prize. Right? It takes a while. Okay, last thing for today, quick one, everyone's favorite, is what we call Compton scattering. More evidence for particles and waves sort of exhibiting the same thing. All right. So, we shoot some light, a photon. We shoot it at an electron. All right. And what happens is the electron ends up, well, we call this the recoil electron. It ends up being scattered out. Well, I guess this is the scattered part. So it ends up bouncing out at a certain angle here and at a certain speed, which I imagine we can measure somehow. All right. Well, the light, therefore, scatters at a different angle. Well, we know its speed because it's light. But what happens here is, if you notice, the scattered photon has a longer wavelength, which means, therefore, a smaller energy. We can still say that. Okay, if it has a longer wavelength and a smaller energy, well, this means it also has, let's see, lambda is h over p. Therefore, p is h over lambda. Now it has smaller, or less, I should say, less momentum and less energy, because this is basically, this is a collision. And in a collision, momentum and energy must be conserved. Okay, so literally this light comes out at a different color after this electron is made to fire out of there. So, I mean, who says that just shining light at an electron by itself should make the electron go anywhere? Well, if the light is treated like a particle, then this is, it's just like, a car hitting a truck, right? Or a hockey puck hitting another hockey puck, right? These are particles, and when they interact, we can apply these classical physics ideas that momentum and energy are conserved, right? But we can treat them now. Well, we can really link the idea that an object can be like a wave and like a particle. All right, so there are certainly problems you can solve here. They are tricky because you have to do both of these things. You have to be able to conserve momentum and energy at the same time. I don't know that we actually have to solve problems like that. Right? What we do have to know, we do have to basically understand this diagram, right? That after a photon interacts with an electron, it's going to lose energy, right? This thing has to have less energy and less momentum than it had before. And if that's the case, well, it's got to have a longer wavelength than it had before. Fair enough? I think that's it, folks. So Monday, we'll basically work with this. All right? Doesn't seem like there would be too many problems to solve there. So we'll do some straightforward. Hey, that's Shags. Come here, you son of a gun, you. All right. All right. So I think that's it, people. Let me just make sure there's nothing in the next one, because I think we're talking about. Oh yeah, I was gonna make an example, and it was like, oh yeah, it's almost time to talk about ham sandwiches, people. I love a good ham sandwich. What is he talking about, ham sandwiches? You'll see. All right. Enjoy. I hope you enjoyed your weekend.